Welcome to the lightning session. I'd like to invite Karu Shiragi up to give his talk.
Well, good afternoon. This is the posters for the lunar test facility development at the Johnson Space Center. Currently is the largest dusty lunar chamber in the US, currently active, is providing a lot of capabilities. One of them is we have two chambers. One is for component testing, goes 10 to the -7, and a 15-foot chamber that was commissioned early on during the Apollo missions was upgraded under the GCD, and now it has a soil bend and IC regulated column that provides a 1-meter drill capabilities, and it has a dust deposition capabilities coming online, and currently is being used for various different ISRU through the companies or industry partners that they're bringing their system for testing. And recently it was one of the carbothermal was reached a TRO5 in this chamber. I invite you to come to the poster session. We have 4 posters, but this is one of the highlights, and it has a QR code for the virtual tour of the facility. So more than happy to stop by and give you more information. Thank you.
Excellent, thank you very much. Next up, we have Sergio Dos Santos Ilucado.
Thank you. So this is one of the 2 projects that were funded under the DARPA NOMAD program with 2 really specific goals. The first one is to convert regolith with minimal Earth-derived additives into structural materials. And then the second one is to take those structural materials and design an orbital structure about 100 meters diameter that can be built out of those with some really tight tolerances. So for the first part, we chose microwave susceptor-assisted casting simply because regolith itself doesn't suscept very well. So we modified that, and we were also able to modify the properties out of that so that we get to different CTEs, different material structures. On the structural bit, it's the zero thermal expansion structure that you see here, and that's really using 2 different materials, whether regolith or metallic structures, to devise a stretch-dominated truss structure that has essentially no thermal expansion and becomes thermally invariant. So we've been able to devise 2 different regolith materials that works, but if you use aluminum titanium, for example, you can build higher symmetry structures than those that are shown here. If you want a boom, a reflector, or some more complex structure that essentially don't react to any temperature input. So thank you very much.
Thank you very much, excellent. Next, we call Parks Easter.
Hello, yes, so I am talking a little bit about the development of a large-scale Lunar Highlands regolith bin at the XLF Lab. So this is currently in development over in Orlando at the University of Central Florida. It is a 10 by 10 meter regolith bin, roughly a depth of 1 meter, and it's going to be including over 140 tons of Lunar Highlands simulant, which is actually LHS2, and that includes a larger particle size distribution. So it's not just all the material under 1 millimeter, it actually has coarse materials in there, to provide a better testing material for rovers and any other tests, drilling, etc. This will have an adjustable regolith depth, so on average 1 meter. We'll be able to make hills if possible. 30 by 30 feet, 10 by 10 meters would take up a large chunk of this room, so there is a lot of room for really large rovers to drive around. It's actually designed to fit at the very least Viper, so it has a very large door. As you can see in the design here, there's actually a workstation crane that the entire bin is designed around, so that will lift rovers into the bin. It will be able to gravity offload to lunar gravity, Martian gravity, whatever gravity you need for your rover. We have a very large team, 20-30 students, that can do any custom terrain, can change out areas of the bin to have different types of regolith. If you want a Martian section, you can do that. It's available for you starting in fall 2023, and it will be hosting the NASA Lunabotics competition. So feel free to check us out in the poster room.
Thank you very much. Next up, we have Christine Gregg.
Hi, so I'm representing the Armadas project at NASA Ames, and we're working on autonomous robotic structural systems for infrastructure on the lunar surface. So our robots and structure, it's based on a programmable matter approach, which means that you can give the system a high-level goal, and it can take whatever form it needs to for a wide variety of applications. So we have small, simple robots that can construct high-performance composite or metallic building blocks, and they can create a range of structures that are much larger than themselves very scalably. The robots use the structure for alignment and metrology, which means that today, with algorithms that are scalable on today's flight hardware, they can achieve high-level autonomy goals. And when we say simple, the idea here is that the robots leverage the structure and can be very reliable even without a lot of sensing. Right now, we're not using any vision or external metrology to do these types of activities. The entire system is built on the assumption that you want to reuse these structures for other applications as we build up sustainable infrastructure. We use mechanical reconfiguration that's designed to do this reuse at an order of magnitude lower power than recycling or other methods of joining materials. And we think this technology could integrate well also with ISRU, since the system is capable of using many different materials and can do general construction with only a few different types of parts. And I want to challenge the common assumption that something like this, high-level construction, is a really far future technology. We're moving past primary structure and showing that you can do outfitting really easily. And quickly with like a Lego style kit of parts. So think wiring, surface interfaces so you don't need surface prep, solar integration, power transfer, plume deflection structures that can be moved, transport systems, habitats. We're looking at a wide variety of integration points, and we're currently looking for folks interested in working with us to enable some next generation applications for infrastructure. So if this sounds interesting, I look forward to chatting with you at the poster session.
Thank you very much. Next, we have Mark Hartigan.
Hey everyone, my name's Mark. I'm a PhD student at the Space Systems Design Laboratory at Georgia Tech down in Atlanta. My advisor is Dr. Glenn Lightsey, and my poster today is part of a larger research project that's with like an interdisciplinary group at Georgia Tech involving our lab, another aerospace lab, some professors from the International Affairs School, and also Georgia Tech Research Institute. So broadly, our research is on developing a scalable cislunar position, navigation, timing, and communications architecture that'll also be interoperable with like current NASA and European Space Agency plans. Some colleagues have already presented some work at places like SciTech and the IAC. And so this presentation, or this poster, will just be a small part and a continuation of that. Specifically, it's on minimal near-term architectures for the lunar South Pole. So assuming there is in a few decades going to be a large navigation constellation for lunar users, how best can we utilize those first few satellites that we send up to be like most useful, because realistically they're not all going to get there at once. And so we've evaluated a bunch of architectures, both from literature and then a few of our own, on the basis of visibility, coverage, gap time, user navigation error, and then navigation performance, and collated together some of the more interesting results to put into our poster. So if you're interested in hearing about any of that research or anything else we're doing, please stop by the poster session. Thank you.
Thank you. Next up, we have Daniel Johnson.
Hi, my name is Daniel Johnson. I'm a PhD student at Colorado School of Mines, where I'm producing a new type of icy lunar regolith simulant called pressure-fused granular, or PFG. It's produced by taking ice, shaving it down, and then sieving the shavings to below 500 micron, and then mixing them in with a lunar highlands terrain simulant. We then put that into a cup and press it with a piston, and we found that by pressing it, we can create fusion between the solid ice grains and the regolith grains, and that by modulating the amount of pressure we apply, we can change the strength properties of the material. So if you look at the plot on the right, when there's not very much water, kind of 0 to 3%, we don't get very much fusion. We get some, but it's not particularly strong. But as you get up to, it looks like it cut off, but up to around 10, 5, 6, 10%, we can create very strong samples, but we don't have to. We can create intermediate strength samples as well. And this is actually really important because historically in the literature, icy regolith simulants have been produced by mixing liquid water with regolith and then freezing it, which produces a fully cemented matrix that behaves like strong limestone or high strength concrete. This leads technology developments for excavation of icy regolith to use technologies like jackhammers and drills and rippers because they're expecting something really, really strong, but there aren't necessarily indications that this wet mixture and freezing method is applicable for the lunar environment where liquid water can't exist. So we're producing this new type of simulant that's highly tailorable so we can test out a much wider range of excavation technologies. And then hopefully when Viper goes up and we actually see what it's like up there, we can then correlate this simulant to what we find up there and do much more intensive testing terrestrially. Thank you very much. I'd be happy to talk with any of you at the poster session in a little bit.
Thank you. Next up, we have George Lordos.
Robots could support many different tasks on the moon, such as extreme terrain access or deploying infrastructure. But if each robot is designed for a specific task, the base could become overrun by a zoo of machines, each with its own unique parts. Next slide, please. To avoid a logistical bottleneck, we developed an open architecture of universal robotic elements named WORMs, the Walking Oligomeric Robotic Mobility System. Each individual worm robot is independent, articulated with its own motors, avionics, and battery. Worms, shoes, pallets, species modules, and many other elements can be easily connected in the field to build capable robots, such as the hexapod shown in the picture. Next slide, please. Every universal interface block, every worm's element comes with a universal interface block so that astronauts can easily mix, match, and snap them together. It only takes seconds to make a secure mechanical, electrical, and data connection. Next slide, please. Using the WORMS platform, many different larger robots tailored to multiple missions can be assembled and even repaired in the field. Missions can include exploring lava tubes, deploying solar panels, or setting up charging stations inside PSRs. Once a mission is completed, a robot can be disassembled and its elements reused by other robots to meet different needs. Next slide, please. A hexapod
You have
prototype,
30 seconds remaining.
thank you, consisting of 6 worms robots, shoes, a pallet, and a species module was demonstrated to TRL-4. This could carry 4 times its own mass on the moon. Other walking gates and integrations with wheeled rovers are also possible to support efficient all-terrain access. And next slide. WORMS is a flexible, efficient, and open architecture for the rapid field assembly of robots. New robots can be literally beamed to the moon and reuse the same hardware over and over, preventing the emergence of an
George, your
ungovernable
time has elapsed.
zoo of robots. Thank you.
Thank you. Next up, we have Alexander Luking. Oops, too far.
We have seen that there are 2 critical obstacles to going and staying on the moon. One is the high transportation cost. But even if you can overcome this cost and land on the moon, you steer up a lot of sharp-edged lunar dust, destroying valuable equipment. But it's not only by landing, but by each kind of mobility. We came up with one approach: moon fiber. So we're starting with the chemical composition of the lunar regolith, and from there we are getting the chemical and physical melt behavior of the regolith through our software model, which is needed to set our parameter for our spinning device. In the spinning device, you only include regolith and energy, and the outcome are soft textiles like this and flexible fibers. The fibers have a thickness of 1/5 of a human hair. But what are the possibilities and the function of those fibers and textiles? We can use it as reinforcement, as the fibers have 26 times higher tensile strength than, for example, 3D prints or sinter bricks, perfect for construction or composites. You can use it as filtration, as those textiles have 100 times higher surface than the lunar rock, perfect for water treatment. And they can be used for protection, as up to 100% of the dust is mitigated if you use this as a landing pad or, for example, as a soft pathway. We have conducted an in-orbit demonstration in early of this month. So we have produced fibers under 0G. Why are we telling you this? Because our next step is going to the moon and validate our technology there, and we are seeking for partners. Thank you very much.
Next up, we have Gregory Maver.
Hey everyone, I'm Greg. I'm a robotics engineer at Maxar. We make orbital and planetary robotic arms. Lunar spacecraft need robust thermal management to perform a myriad of tasks aimed at establishing a sustained presence on the moon. Many of these tasks also require robotic arms like those Maxar supplied to NASA and other customers over the past couple decades. So a question that we're thinking about is how can we utilize a spacecraft's existing robotic arm or arms, primarily used for mission ops, to relieve some system thermal constraints? You can consider the Apollo Lunar Rover, which is the bottom left graphic on the slide. That's a system where astronauts manually moved reflectors, radiators, and dust covers to reconfigure the spacecraft to optimally survive the lunar night. Meanwhile, robotic arms have been capable of manipulating payloads on planetary spacecraft for years now, maybe most recently on the InSight lander. So we're thinking, relocating instruments and or thermal components like radiators, as we've got depicted in the A insets here, is one way we could use robotic arms to perform some thermal management duties. Another way, shown in the B insets, is we can use them to position covers to retain or dissipate heat. Of course, the arm itself has to survive the lunar environment as well. So we've got shown up there the sampler arm, which is a Maxar-built robotic arm being hosted on a future NASA CLIPS mission. It utilizes a traditional thermal management system consisting of heaters, thermistors, and blankets that total about 350 grams for that 4.5-foot long 5-DOF manipulator. In the lunar environment, arms with conventional thermal management tend to leverage existing energy storage and power systems already required for the spacecraft, and this allows us to avoid using cryo-capable components, which are exotic and have some disadvantages. So yeah, there's an opportunity to optimize battery capacity and deck space here. That's what my poster's about, so come find me in the poster room.
Next up, we have Jacob Ortega.
Hello, everybody. I'm a first-year PhD student at Missouri S&T, and I'm here to talk about our project, Lunar In Situ Aluminum Production through Molten Salt Electrolysis, which was a winner of the NASA Big Idea 2023 competition. We are leveraging a currently existing Luster 21 project to get beneficiated anorthite and convert that beneficiated anorthite into aluminum metal, water, oxygen gas, and sand. So to start, we started by cannibalizing the existing process, the FFC Cambridge process, which was well developed by Drs. Frey, Farthing, and Chen at Cambridge University. And we modified it to fit for aluminum, and then all that will be tested on our campus using our facilities. But this project is very early, so we're still under the development phase. And if you have any questions, feel free to talk to me about my poster session.
Thank you very much. Next up, we have Aaron Paz.
Thank you. So I'm going to talk about the Carbon Thermal Reduction Demonstration Project, or CARD. It started, we're building off of some work from 2010. That was an ISRU field demonstration that some of us like to call the dust to thrust demonstration, where we actually took Hawaiian tephra, that's a local material in Mauna Kea, has a chemistry very similar to lunar regolith, and processed it in a carbon thermal reduction reactor that was brought by Orbitech, who is now part of Sierra Space. Concentrated solar energy developed by Physical Sciences Inc. was used to melt the regolith, where it was reacted with methane to make carbon monoxide, brings oxygen out in the form of CO, which is then reacted with hydrogen to form methane and water, which we then split into hydrogen and oxygen, dried the oxygen, liquefied it, and used it to fire a thruster at the end of the week. So it was about a 10-year gap from then to what we started picking back up. So around 2020, We're now picking up where we left off. Our goal with CARD is to try to take some of these aspects and raise the TRL from 4 to 6, which otherwise is known as the valley of death. So we appreciate the challenge, but accept it and have had some success. A couple months ago, we tested the carbothermal reactor in a vacuum chamber. We used a 2 kilowatt laser to melt the regolith. We extracted the oxygen and we're able to quantify the yield using a gas analysis system developed by Kennedy Space Center. It's based on a COTS version of the M-Solo instrument that is on the manifest for Prime and Viper. Next, we're planning to develop our prototype, which will focus on an automated reactor being developed by Sierra Space through a tipping point. We'll pair that with a solar concentrator being developed by Glenn Research Center and the optical energy routed through a waveguide developed by Physical Sciences, Inc. And the end goal is to be able to make oxygen. Eventually, this can be scaled up. And when scaled up, this could make several times its own weight in oxygen every year on the lunar surface. Thanks.
Thank you so much. Next up, we have Amy Quartaro.
Hi, so like she said, my name is Amy Quatero. I am a PhD student at Virginia Tech with the Field and Space Experimental Robotics Laboratory. And so I wanted to talk a little bit today about the slide that poorly formatted on this screen. So the focus on my research and kind of the direction of the Phaser Lab at Virginia Tech. So we're looking at lunar construction, outfitting and maintenance and assembly. So a lot of that work done thus far and a lot of the interest is in rigid element construction, ISRU-based, very structural elements. So then coming after that is kind of the outfitting and maintenance. So my particular interests are in looking at cables and flexible elements, things that are very present in space, very present in construction, but are really difficult to manage and are really difficult to kind of incorporate into this high-level planning. In order to have a robotically constructed and maintained facility, robotics really need to be able to handle those types of flexible elements in tight, cluttered environments. And so my approach to that is to do a dynamic model. And so we're looking at this one on the left with the quick video. And so just to kind of illustrate how difficult a problem that really is to have in a tight environment with a high fidelity robot. And so then another problem that comes out of that is if you have to have such a small high fidelity manipulator in there, how do you actually move one precise system from maintenance A to B to C? How do you actually move cables from a spool all the way down to make a power grid and have it on your solar array? And so we're looking at ways to do that with heterogeneous robot teams, specifically looking at large, low fidelity, but large workspace manipulators with small robot teams and kind of how those interplay. And that's a lot of the hardware capability that we have at our lab and kind of what we're looking at down the line for autonomous robotic infrastructure. And I'm more than happy to talk about this more in front of my poster. And I apologize that the slide did not seem to format properly. I tried to make it really nice, but thank you.
My apologies, Amy. I'm sorry I didn't catch that.
It looked nice on PowerPoint.
Next up, we have Paul Van Suzanne.
Good afternoon, everyone. It's me again. Anyway, so you just heard all about the Luster Grant, and there are two posters in which I explain more about several different aspects of that. This particular one is about the field testing component of that, our preparation and our adventures. I could write several books about them. As you can see, the titles are listed here. But anyway, so we are prepping field tests for ground penetrating radar. So our adventures there, building targets during our winter, also making our robot fly to get a full depth 1 meter test without being able to do the winter test that we wanted, and our data that we got from that. And then specifically also what we would have done if we would have gotten a good winter and what we're going to do next year when we will get a good winter. So come talk to me at my posters. The other poster, by the way, is about the thermal profiles of cryo volatiles. So come see me at the poster. Thank you.
Good afternoon. The Dynetics Human Landing System provides the imminent and practical capability to safely and repeatedly deliver up to 4 astronauts and payload to the lunar South Pole for stays up to 30 days in support of NASA's Artemis missions and commercial customers. The Alpaca lander can safely access the most extreme lunar terrains on slopes much greater than 10 degrees with lander self-leveling, closer to sites of interest, negating the need for lengthy EVA excursions. The low-slung design for all-moon access places the 3-meter diameter crew module's EVA hatch approximately 2 meters and a few short steps from the hatch to the moon. As a benefit of the low-slung design, Alpaca is uniquely capable of surface docking called shirt sleeve transfer, which allows the surface elements such as a pressurized rover to dock via an extensible tunnel to the crew module, eliminating the need for EVAs to transfer between elements. This dramatically improves crew safety and allows the EVA time to be spent on exploration and scientific endeavors. The cargo variants maintain a common flight structure and reusability enabled by propellant refill and NRHO, and can repeatedly transport over 12 metric tons of payload to the moon. The 3-meter cargo Alpaca, or the extended 5-meter cargo Llama, can also land and pick up over 5 metric tons of payloads from the surface for return back to Lunar Gateway. For one-way trips, Alpaca can deliver an astonishing 30 metric tons, such as large habitats, mining or construction equipment, or a megawatt nuclear reactor directly to the lunar surface. Remaining on the surface, Alpaca can provide power, protection, data and communications, and structural support for years. Integrated inflatable modules can vastly expand habitable space. When ISRU production is underway, Alpaca can serve as a tanker to return more than 20 metric tons of heavy LOX to a propellant depot, with only the lightweight methane delivered from Earth. The technologies developed on this program supports NASA's Moon to Mars initiative, and we are extensible to other exploration missions. This is real, this is possible, and Dynetics is ready. Please come by the poster sessions to see how we can enable your mission.
Thank you so much. Next up, we have Melody Yasher.
Hi, everyone. My name is Melody Yashar. I am the Vice President of Building Design and Performance at ICON. ICON is a construction technologies company based out of Austin, Texas. We develop large-scale additive manufacturing solutions for both Earth and space. We were recently awarded a Phase 3 SBIR for what we refer to as Project Olympus. And as part of the, Project Olympus and its surrounding research is in support of the IMPACT program, which is the Moon to Mars Planetary Autonomous Construction Technologies project based out of Marshall Space Flight Center. As part of the IMPACT project, we at ICON are developing a robotic construction system using directed energy deposition methods that utilize 100% ISRU regolith to manufacture various types of construction elements on the lunar surface, beginning with horizontal construction elements and then eventually getting to vertical construction elements. To get to the subject of my poster, we are currently developing what I refer to as a morphological approach to lunar base planning, which models key infrastructure elements in a foundational lunar base using a development logic which is parametric and adaptable in nature. This model essentially develops a 4D BIM, meaning a time-based building information modeling platform for urban scale simulations which parallel our terrestrial master planning and urban development work, utilizing additive manufacturing to develop communities of homes and new infrastructure, ranging in the scale of hundreds to thousands of structures. Naturally, the parameters are quite different for Earth and space, but what they have in common here is that a 4D BIM morphological approach can help synthesize multiple priorities and interests from science groups, government, defense, and nonprofit institutions, and will be essential for identifying optimal land use strategies, identifying possible regulatory zones that we want to, and also anticipating and avoiding very costly mistakes. Thank you.
Thank you so much. Now it's time for us to switch to our online presenters, starting with Veronica Acosta. Veronica, are you ready to go?
I think I am. Are you able to see my video?
Yes.
Can you see me? Okay, great. Thank you. So as we get ready to go back to the moon, we must not overlook the critical and challenging role of communication. Limited bandwidth and delayed and disruption in space pose challenges to real-time data transfer. And as some of you already know, NASA has proposed the use of delayed and disruption tolerant networking, also known as DTN, to enable internet-like communication capabilities on the lunar surface. But DTN presents a new challenge for space organizations as it requires new protocols and architectures to become operational at scale. Now, this ties back to what Spuds highlighted this morning, specifically the lunar infrastructure goal and objective number 2 for developing a moon-to-earth communication architecture. And this is where the Spatian DTN platform comes into play. It aims to enable space and ground assets to connect and transfer data efficiently, supporting multi-administration and interoperable network overlays with a configurable DTN managed network solution. Now, what this means is that you can create networks where different organizations participate on an internet-like environment. And also through the Spatian managed instance, nodes can be converted into a DTN capable node, enabling organizations to move towards the LunaNet compliance in networking services. As we prepare to go back to the moon after more than 50 years, communication must not be overlooked. If you're planning on sending rovers to the lunar surface, working on astronaut mobile devices for real-time image processing or space station communications, among other things, it will be of great advantage to make them DTN compliant now in preparation for LunaNet. I, along with our CEO, Alberto, will be at Gathertown to answer any questions or comments that you might have. Thank you.
Thank you so much. Next up, we have Nihant Adina. Nihant, are you ready?
Yeah. Hello, everyone. I'm Nihant Adina, a PhD student at The Ohio State University, and my advisor is Dr. Jin Wong. And shout out to Jeffrey Snack from NASA, who's our PI. My poster talks about the design, protection, and control of lunar surface DC microgrids utilizing WBG-based flexible DC energy router. I'm just going to introduce the router because of the time constraints. As you can see on the middle, you can see the modular DC energy router circuit diagram, which has 3 arms and has submodules in it. So it's a modular and a scalable power management unit, and it has integrated energy storage. And we've selected gallium nitride hemmed devices, the semiconductor devices for our submodules, which are actually radiation hardened. And also we've actually, you can see down, it's the assembly of the energy router. We have tested and verified the submodule, single submodule in vacuum and cryogenic conditions. And in the end, it's the energy router is actually an all-in-one solution for microgrid power management requirements, for stability enhancement, power flow control, fault protection, and reconfiguration. And on the right, you can see our Envision Lunar DC microgrids, which has 4, which is the habitat, the charging stations, the ISRU, and the LSC, which are connected in the ring architecture. And we're currently in the 2nd year of the project, and we're building a microgrid test bed at our facility. And we're going to test out the different functionalities of the energy router. And finally, I just would like to shout out our team members from Ohio State and Raytheon. And if you would like to know more or have any questions, please find me at Gathertown. Thanks a lot for this opportunity, and have a good day, guys.
Thank you so much. Next up, we have Vijay Devarakonda. Could you please confirm you can turn on your audio and video?
Yeah, can you hear me okay?
Yes, sir.
Okay, so yeah, the title of my presentation today is Filtration and Collection of Lunar Dust, and my name is Vijay Devarakonda. I'm with a small business called Analytical Scientific Products based in Dallas, Texas. This project was a part of a phase 1 SIBR with NASA that we just completed. So the objective here was to take the dust-laden gas in a spacecraft environment and remove the dust particles and collect them in a bag and send the clean, dust-free gas to the rest of the process, like ISRU processes. Our technology is, it uses a combination of fluid mechanics and electrodynamics to remove the particles from the gas phase and to direct them into a dust collection bag. It is independent of the type of the source of dust, so we can process both the dust originating from outside the spacecraft and the dust generated by the cabin inside the spacecraft. So as a part of this project, we performed analysis, engineering calculations to design the filter and the operating conditions. Then we fabricated a breadboard version of the filter. And we also developed a test rig where we could expose the filter to different levels of dust concentrations. And we also developed optical instrumentation to probe the dust aerosol that is entering the filter and exiting the filter. We performed about 30 tests where we varied the dust concentration that goes into the filter and what is coming out of the filter. And sample data shown in the top right, where the dust concentration entering the filter was pretty high, up to about 180 milligram per meter cube. And the filter was effective in removing most of the particles. So the concentration exiting the filter through the clean gas was only a few milligram per meter cube, as you can see in the top right. So in the 30 tests, we got...
I'm afraid your time has elapsed.
Okay, thank you.
Thank you. Next up, we have Britt Duffy Adkins.
Great, thank you so much. Hi, everyone. My name is Britt Duffy Adkins. I am the, can everyone hear me and see me okay? I'm getting a message here.
Yes, we can hear you.
Okay, all right. All right, well, maybe it's not important to see me, that's fine. So I am the founder and CEO of Celestial Citizen, a space urban planning company that is on a mission to build sustainable space communities by bringing together people, systems, and technology. So Celestial Citizen seeks to support lunar surface operations by integrating technology, infrastructure planning, architecture, city design, while also focusing heavily on public outreach and engagement in the development of a planning strategy. So today, I'm excited to talk to you about sort of the methodology and the way in which we would go about this. So as you see laid out here on the slide, we have a few different areas, both the planning process, infrastructure, systems integration, public participation, and then also building community through future visioning as sort of our key tenets. I believe that space urban planning is an emerging and critical focus area, and especially with the increasing commercial and governmental activity that is planned for the lunar surface in the coming years, we need to focus on not only the long-term objectives as well as the short-term realities when it comes to that foundational layer of what might someday become the first lunar base or research community. So for context, urban planning can be defined as the design and regulation of the uses of space, focusing on physical form, economic functions, and social impacts of the environment, as well as the engineering, architecture, social and political concerns that go along with building out a community. So space urban planning is really a transdisciplinary approach to all of these things. I know I'm running out of time here, but it would be great to connect with folks on this particular topic. You can reach out to me at brit@celestialcitizen.com. Please check out our website and get in touch if this sounds interesting.
Thank you very much. Next up, we have Claudia Jimenez Cuesta.
Good afternoon. Can you hear me?
Yes, we can.
Hello, my name is Claudia. I'm joining today from Glasgow, the UK, and I'll be presenting the research that we're currently undertaking at the university. Next, please. We are focusing on the flow physics regarding spacecraft landings, particularly the dust cloud that is formed as retropropulsive thrusters are fired. Next slide, please. Our main objective is to characterize the dust cloud in terms of its region of influence, particle concentration, and particle speeds. And we will do this, next please, through diagnostic techniques such as edge detection, light scattering models, and particle image velocimetry. We will carry this research, next slide please, in the vacuum chamber that we developed in collaboration with the European Space Agency. However, pumping down this facility is very energy and time consuming. So we've designed a proof of concept experiment. Next slide, please. This experiment consists of a solenoid valve that impinges on a bed of regolith simulants, and the dust cloud is captured by a high-speed camera. Next, please. This experiment will be used, well, is used to test the capability of a edge detection algorithm that we're working on. These are the 3 steps involved in the algorithm, and we use that to characterize the region of influence.
You have 30 seconds.
Of the dust cloud. Next few slides, please. And the next ones, please. We can see, sorry, that's my supervisor there. We can see the dust cloud that results and the edge detection carried out. And lastly, we will be now adding cameras and laser sheets to reconstruct the 3D cloud. Thank you.
Thank you very much, Claudia. Sorry.
Thank you.
Next up, we have Liam Morrissey. Liam, are you ready?
Yes, can you hear me?
Yes, sir.
Great. Thanks for saving the best for last. So I'm coming from Memorial University in Canada, partnering with NASA Goddard, in particular, Prabal Saxena, Jason McLean, and Rosemary Killen, where we're basically suggesting the use of an in-situ artificial substrate witness plate. We know that there's a goal for long-term sustained efforts on the moon, but we would argue that to actually make these viable, we need to better understand surface processes on the moon and how we are changing the surface of the moon. And that's not an easy thing to understand. So what we're thinking is that we can use these biscuits as a way to sort of work as a witness plate. They're low cost, they're low mass, and most importantly, they produce a low environmental footprint. And basically what you can do is you can lay them in strategic sites, you can characterize them pre and post exposure, and you can understand either from a scientific point of view, what is the lunar space weather condition like, or perhaps more importantly, from an operational point of view, which materials are actually surviving best in that location. So sort of in that vein, what I've done is I've worked on a case study where I'm modeling an aluminum biscuit interacting with what we expect the solar wind to look like for an exposure duration of 10 years. And spoiler, these biscuits are able to sort of have an identifiable change after a relatively short period, such that you could sort of use them as a way of in situ material characterization or a low-cost way of assessing different options, coatings, metals, surfaces. So I encourage you to come by my poster. I'm happy to chat more, and we actually have a paper that was just submitted trying to get this concept out there for the community. Thank you for your time.
Thank you.
Is that the end, really? All right. Cool. I will switch microphones. Can we get a round of applause for everyone online and in the room? Thank you so much. Those were really super exciting. I'm like, now I want to make like a coat out of moon fiber fabric. That's so cool.